period today to do a test. So we'll be at, hopefully get through the material that we need. So the last thing that we talked about were the sources that where the nebulizers were created and flame atomization. And the one that's similar to what we have is this one at the top. It's top left. This design. So it's just a high pressure gas flow. There's a small needle that's hooked to your solution. So you got a solution down here, and it's going to draw that solution, put it across the gas, and mist it. If we look at the other thing that varies with flames, is that the temperature of the flame is going to vary with depending on who the oxidant and readjuctant are. We're starting that. But yeah, so. So if we can change the gases around, we can get different temperatures. So going from something like natural gas air, which is what a Bunsen burner is going to be, that can get you 17 to 1900 degrees, depending on whether you've got the flame leaned out or burning rich. So anytime you have a fuel oxidant mixture, the exact temperature is going to be determined by whether or not the flame is rich or lean. So let's make sure we know what those terms mean. So what does it mean for something to be running rich? Excess fuel or excess oxygen?
Fuel, right?
Okay, so if your car's running rich, it's got a flooding smell. You smell gasoline coming out of the tailpipe. So here that means there's excess fuel. And the converse is true. For something that's running lean, means that there's excess. Say again?
Running like a two-stroke engine.
Yeah, like it's not the oil. The two-stroke has the smell because the oil that's in the gas, and they always smoke to some extent. But like if you adjust the carburetor settings on you can have it so that less fuel goes in with the air that's coming in it, and you can adjust the ratio of fuel to oxidant. So typically you do that with something called the jet on your carburetor. It's an adjustment. Today's computer-controlled cars, it's controlled electronically. But the same's true when we talk about our flame. As I change to put more natural gas in, it becomes a rich flame. It's going to be a little lower temp. If I shut down the gas flow and off the oxygen up, it's going to burn a little bit hotter. Now, natural gas and oxygen burn or air burn at a pretty low velocity because oxygen's only about 22% of the air at sea level. If I'll just take and switch the oxidant to 100% oxygen, I can gain almost 1,000 degrees in temperature. And the big thing, the burn velocity now increases by a factor of 10. So your flame's going to have a roar to it. When you start getting burn velocities exceeding 1,000 centimeters per second, so 1,000 centimeters per second, you're in the explosive range. So that's something we have to be careful of with our instruments as well. The same's true hydrogen and air. It'll get you to about 2,000 degrees, but now the burn velocity's up there pretty good. If I switch over to hydrogen and oxygen, I can get another 400 or 500 degrees out of it. But now I've got a burn velocity that's in the explosive range. So I have to really be careful if I'm using hydrogen and oxygen that all the gases are consumed in the flame. Now the main one that we use, where do we use these at? So if I'm doing flame emission, this is the one we can get away with. That's a low enough temp that typically I can use the alkali metals and the alkali with natural gas airflame. What we use in atomic absorption spectroscopy are acetylene air, so flame AAS. We have a mixture of acetylene and air, so now our burn temperatures are up in the 2,000 degrees range. and this one burns pretty slow. If I wanted to take the temperature up, I could go to pure oxygen, and the temperature would be over 3,000, but the burn velocity is so high that if something went wrong with the gases, I've got a huge grenade. So we can't have that. So to have things more controlled, what we do is we switch to acetylene and nitrous oxide. So the same stuff they put in a race car, nitrous oxide. There's a big tank of that in there, and that can get us to temperatures about 2,800, but the burn velocity is down at about 285. It's still very acceptable and controllable. So another thing we have to think about, do these gases that are in the flame, do they absorb at the wavelength of interest? So natural gas is not going to, if we think about natural gas, it's primarily mixtures of methane and ethane. So CH4 and C2H6. And those are not absorbers in the UV vis, not absorbed in UV vis. But if you look at something like acetylene on the other hand, has a triple bond in it. And anytime you have extended conjugation, a double bond, a triple bond, those are going to be things that do absorb. So this is a strong UV absorber. We have to make sure that it's not going to absorb at the wavelengths that we're going to analyze at, or we have to completely consume all of it. So if I had something that absorbed strongly down at 220 where acetylene absorbs strong, I'd have to make sure that I'm running a pretty lean flame, so I would consume 100% of the acetylene going into the torch. So lower temperature flames, they're hot enough to get emission spectras for the alkali and the alkali earths. And that's a lot of the common metals that we have. So things like lithium, sodium, potassium, magnesium, calcium, strontium. Those are some of the common things we need to look at all the time. So there's a simpler technique that we can use on those. Like I showed you yesterday with the water being sucked into the flame, the bright orange glow, you just look at that particular wavelength. But if you want to look at the heavier metals, you've got to take the temperature up closer to the 3,000 range to excite those heavier metals. And something else about flames, we have to realize they're not uniform in composition, in length, or in their cross-section. Temperature can vary quite a bit over these different regions. So there is a region that we call the preheat region. So coming right on the top of the burner, there's going to be a small little point here that typically, if you look at a flame burning, like if you look at a match burning, you'll see the flames not on the wood. The flame is dancing above the wood a few millimeters. Okay, that's the region where the compounds, the hydrocarbons, are mixing with air. It's starting to preheat, right? The next reaction is that's typically the primary blue that we see. It's called the primary reaction zone. So mainly emitted from this are CO2, the product of combustion for hydrocarbon and water, or oxygen, which are CO2 and water. We have carbon monoxide and some nitrogen gas and water emitted as molecular species. And again, molecules that absorb broad spectras are their problems. So that's the primary combustion zone. And then there'll be a fainter blue that's surrounding that, and typically significantly larger, called the endoconal layer. And this is where you start to get your thermal equilibrium. So this is the inner conal layer that's inside of here. And then typically on the outside of that, you're going to have what's called the outer cone, and that's the secondary reaction layer. So it's going to be the outside tip of the flame. Now, the key thing is we're going to take our measurements because of the thermal stability. We're going to be somewhere inside of here. That's where we're trying to do our measurements at. And this just gives an example of how much a Bunsen burner can vary. So here is a profile thermal image of a Bunsen burner, and you got the tip of the burner, which is a centimeter wide or so, and going up a centimeter, you're changing now from, this is our lowest temperature is 1400 degrees, in a period of about 2 centimeters going to almost 1900 degrees. So you got a 500-degree swing in 2 centimeters. Now, if you go out on the radial side of it, it's even higher, the swing. So now if you go from now going a little over a centimeter in width this way, from dead center, you're dropping 300 to 400 degrees in temperature. So where we shine our beam of light through the sample is absolutely critical. So do we shine our beam of light through this part of the flame? Do we shine it down through here? Do we put it up here at this point? One of the problems down in this region is that it's changing quickly. We're wanting so that we have the biggest region of thermal stability. So we want these bands to be separated as much as possible. That way, as the flame flickers a little bit, we'll have the most stability. And alignment is one of the things that's absolutely critical. You've got to know where to put the beam inside of the flame. And I'll show you that when we do our experiment next week. If temperatures are too hot, it can cause the ionization of the metal of interest. And we're in atomic absorption spectroscopy, we're trying to quantify the neutral metal atoms. So ionization, where we would lose electrons off, okay, that is something that's not desired. So we don't want this to happen. We want to keep everything in the form of the neutral metal. Different elements have different positions inside of the flame. So this gives you an example of 3 different elements. Start with chromium first. Chromium has the highest absorbance, as low in the flame as you can get. Silver is the opposite. Silver, the higher and higher you go in the flame, till silver is going to plateau out. Magnesium in the middle has a certain height, about maybe 1.5 centimeters up or 1 1/4, where it reaches the maximum. This is the point you would want to do the measurement at. Some of the more modern instruments that have XYZ controllers that are robotic controlled, that it knows where the beam of light is, it automatically, when you choose element silver, it automatically positions the burner exactly where it needs to be. What we have to do with ours is put a low concentration of silver in the sample, and we have to manually manipulate a XYZ translator to get the flame to exactly the right height in the beam. So one way or the other, you have to optimize that to get the best sensitivity out of the analysis. All right, so here's what ours looks like yesterday. I don't know if you remember looking at that very closely. So here was the burner at the top. That's where all the action was. At the bottom, this is where the sample came in, a capillary, and there were a number of gases going into it. There was the oxidant coming in that's going into the nebulizer, and that was just compressed air with ours. There was a tank of acetylene that was coming in, and there was a knob that we could control out here on the end that controls how much the nebulizer flow rate is. So normally it's flowing in the neighborhood of 3 to 5 mils a minute, but that's something that you can adjust. And then there's an auxiliary oxidant, so if I wanted to add an NO2 to it, I could kick up the temperature and add nitrous oxide to the sample. So the idea is that the mist is being formed right here in the atomization process. And there's these baffles in here, and the baffle's job are the small droplets. It's trying to let them hit these and fall, or the big droplets hit those and fall out of solution, or out of the mist. The big drops are hopefully going to come out, and they're going to come down this drain and go to the waste. But the small aerosols are going to continue to go up here, and now they're a mixture of both the fuel, the oxidant, and the sample. It's got everything together. So it gets to the top, you're going to have ignition, and it's going to burn. If you set the gases wrong, what will happen is you'll get what's called a backfire. A backfire is when the flame ignites somewhere down in this region. And these are, because something like acetylene gas is very flammable, even with air. This instrument is designed, is put together with O-rings so that all the pieces are tethered to the side. You'll see that. So they've got a piece of wire that's tethered to the side. So if this thing does happen to backfire and blow apart, there's pieces of aluminum foil that are here that are pressure valves. It's going to blow those so it won't build up a lot of pressure on the inside. You don't want this burner head, which weighs, it's a chunk of titanium that weighs a couple of pounds. You don't want it flying across the room at a couple hundred meters per second. Very stable design. They work well. Great reproducibility. The disadvantage is they're not as sensitive as what a furnace is. So if we look at a flame atomizer, what does the sample have to be introduced as? So what did we talk about there? All right. So y'all went with B. I like that. I'm going to give you credit for it. We didn't talk about gases. It has to be a liquid, but if you had a gaseous sample, you could introduce a gas straight into it.
Well, it'd just be the same thing as like the acetylene that's like you're burning off, right?
Right, yeah. So if you had a sample that was a gaseous sample, so if you took and put in mercury, you can heat up mercury just a little bit and take mercury into the gas phase. You can introduce that gaseous mercury directly into it. And there's only a couple of elements that are metals that you can do that to. But in particular, you can do mercury, and arsenic's another important one that we do. Arsenic itself is not volatile, but arsenic can be converted into a hydride, which is gaseous. Okay, so there's usually we think of just liquids, and that's the reason I'll check that one. But also, if you did have something that was a gas, we'll actually do both. But oops, too many jumps. All right, so now moving to the next type of analyzer. We talked about the flame. The other side of the picture is going to the electrothermals, which are what I call graphite furnace. That's the common name that we've accepted for them. And that is the technique that's being used to create the furnace. So GF, graphite furnace, or electrothermal. Either one of those, they mean the same thing. These first appeared in the markets in the 1970s commercially, and today they've really become commonplace. They're used in both atomic absorption and atomic fluorescence. And the reason they have better sensitivity is because the entire sample is atomized in a short period of time, and the atoms remain in the cell for a longer time period compared to the flame. Okay, so let me just go back and think about the reference to that. When you've got this sample coming out of the flame, you've got this little beam of light you're shooting across here. And your samples are going to be exposed in that, since this has a burn velocity in the hundreds of centimeters per second range. Your sample, each individual atom, is most going to be exposed to that beam of light microseconds to milliseconds. It's going to be a very short period of time. So each individual atom only gets a small chance that it's going to absorb light in the system. But furnaces do it a little bit differently. And because of that, furnaces use a small amount of sample. Typically, you're only going to put a couple of microliters in. You evaporate off the solvent at a low temperature. Then you ash the compound. You burn off the carbon materials, typically at a temperature around 550 to get rid of the carbon materials. Carbon gets converted into CO2 and water. And then you'll rapidly ramp the temperature up from anywhere from 2,000 to 3,000 degrees in a few milliseconds. And when you do that, you vaporize the metal atoms, and they go into the gas phase, and the absorption light occurs directly above this heated surface. All right, so here's kind of an idea of the temperature ramp. So you would start off at ambient temperature. You would put a couple of microliters of the sample in. You would ramp it up to the boiling point of your solvent, which is typically going to be water, so 105 degrees. And then you would allow the water to vaporize off for a minute or two. And then you would ramp the temperature up over a couple of a few seconds at about a rate of about 50 degrees a second. That's going to burn off any organics. And then once you allow it to ash for maybe a minute or so, then you're going to rapidly crank up the temperature to 2400. That's going to vaporize the sample, and you're going to look at the signal once you're vaporizing the sample. So the way that this works is that you control the temperature by passing current over a graphite cylinder. So, hence the name graphite furnace. Here's one of the cylinders. So this is actually a broke one. This is where the heating component comes from. And graphite itself is not a good conductor. And inside of that is where this tube fits, and where the little hole is where the sample goes inside of that tube. So that actually fits inside of this guy, like that. So here's what the furnace looks like. And then the sample is going to go in the hole in the top. This is going to be the tube. And then the sample is going to line in and go in there. So you pass the current across this thing, the bigger chunk of graphite. And when it goes across there, it's open on both ends. And we have a very high current power supply that's going to vary the current flow to control the temperature across it. So if we look at what this looks like in a profile, you've got your graphite furnace that has electrical connector on each end, like so. It's got to have some insulator to try to keep the whole thing from getting too hot. And you're flowing water around this thing, in and out of it, so you've got some kind of a cooling system. So you could have tap water flowing in and flowing out like maybe you would do on a condenser. Most of the things have something like a small radiator to keep the water at a pretty low temperature. And then you also have a gas that's coming in, and typically that gas is going to be argon. And the gas comes in, and it's going to carry the sample out the open ends of the tube. So the gas is going to, as the sample is converted into a vapor phase, it's going to carry that out. Then the light itself is going to be passed along the long axis of the tube, and this is where the absorption is going to occur. So you're going to have a pinon in one side, a P on the other side, and the ratio of those two is your percent transmittance. So as your sample atoms get vaporized and they float out of this tube in both ways, they're going to absorb some light. So if we look at the role of the carrier gas, it's typically argon. It prevents things from coming in the tube, and it also carries the vapors out during the process of atomization and the heating stages. So if we look at the steps we are, this is kind of like I showed you on the other one, and I'll just show you a little bit more in detail. First thing you're going to do is put your sample in, you're going to dry it. Then you're going to take the sample up to a high enough temperature that you're going to ash it, pyrolyze the sample. Then you're going to allow it to cool just a moment, atomize it, and then after it atomizes, you're going to let the temperature stay up there long enough that all of the sample is blown out. Okay, so it's a clean out time. And then you've got to allow it to cool to room temperature, and you use argon gas as your purge. The real big reason for the water is the cooling. Otherwise, you would run a sample. This thing glows cherry red. When it heats up so much, gets up to 2,400, 2,800 degrees. If you just let that cool on its own, you'd be 30 minutes between samples. Okay, but the water running around the outside still takes it about 5 minutes to cool down. Cool enough, you can start again. But that's the purpose of the water. All right, if we look at the output, this is an example of an output that we would have. So in the first couple of things they put in here, these are standards at 0.05, 0.1, and 0.2 micrograms per milliliter. So if we think about that, that's a part per million. So this is, if we want to, this is 50 parts per billion, 100, and 200 parts per billion. If we look at the relationship, there's a relationship between the height of the signals and the concentrations. So these are standards that we have in these first three. And then on the other side, this is a sample that was put in. This is actually orange juice that came out of California. I told you all a little bit about that. And they found that the orange juice contained a significant amount of lead in it. The standards here are lead. And when they started looking at this, they found out that they put the sample in, it ashes it, and then they pyrolyze it, so it's burning off all the organic compounds in the orange juice. And then they atomize it. The signal that comes here at this point is the signal that's due to the lead. Okay, so this is the signal that's due to the lead, so you just simply go across and see where you are It's a little bit more, somewhere between, I'd say, maybe 55 parts per billion lead in the juice. Now, if you had one serving of juice, would 55 parts per billion hurt you? No. If you had 5 servings a week for a couple of years, yeah, that's enough to bioaccumulate and cause damage to the body. But this is how you would apply that particular technique. All right. Now, the advantage to graphite furnace is that the detector, as it rises to its maximum temperature in a few seconds, and then the signal decays back to 0. So that's you rise to here. This is only, it goes up a second or two and then quickly comes back down to 0. Typically, it's going to be less than a second this change is going to occur, so you have to have a fairly high-speed data acquisition system. You want it to sample maybe 100 times a second. So you would have a sampling frequency of 100 hertz. And typically, you look at peak height, but you can also do the analysis based on peak area. Now, the advantage to this is that there's a little bit less sample preparation. If you've got a semi-solid or even a solid material, if you put it in there, you can deal with it. Right? Not a problem. You just have to manually put your sample in there with tweezers. If you don't have very much sample available, because we only use microliters at a time in the analysis, it's highly sensitive. Where the flame instrument, you need a minimum of 10 mils of sample. And usually you have at least 100 available to you. The limits of detection are in the neighborhood of 10 to the minus 10th to 10 to the minus 13th grams, and that depends on each element. And this is because we're dealing with such a low volume, it's very easily automated. It's easy to move around a few microliters at a time with pipetters and syringes. Now, it doesn't have all good parts to it. Disadvantages to it is that the coefficient of variation is typically in the 5 to 10% area, where a flame is typically 1%. It's slower. On the flame, there's very little memory effects, so you can go from sample to sample to sample in a matter of seconds. On this one, you've got to let it cool down, so it takes a while to do an analysis. And there's also a decreased linear dynamic range. Typically, you're limited to a minimum or maximum of 1 order of magnitude. So what do I mean by that when I say you could calibrate maybe between 50 and 500 parts per billion. And if you went higher than that in concentration, you would lose linearity. So typically you've got times 10 of whatever your lowest one is, and that's the absolute most you can do. Okay, so how is the temperature controlled by the atomizer? What did we talk about there? All right. So 50-50. Some said A, B, and it's the passage of current across that furnace body. A, B is how it's controlled in a flame, but in a graphite furnace, there's no flame there. All right. Let's look at one right quick. So let's water next door. It's got me in here. So the flame instrument that I showed you, that also has sensors to it. That is a graphite furnace. So this is the graphite furnace. See where it's set in here. So it's going to put it right down inside here where the burner head is. The sample is going to go at the top. The sample is going to go right down inside there, and the black is behind it. So this actually has a cooler hook to it down here on the bottom somewhere. There's a cooling tower. You go down the side. It's got air that blows across the radiator. Circulates the water. And the way that this one works is this is what holds the sample. So this sits right in different standards of operation to the sample, and it will draw up a certain volume. This basically has a syringe of this in, and it can plug microwave closet right inside there that might come out. The other thing that's neat that it can do is it can have one standard made up. It can dilute that standard. So it can pull up a 10 microliter standard in 10 parts of 9 parts of water, 1.5, whatever. So it brings one standard precisely bought. So this instrument is actually switchable between two graphite furnace. But we had another company, Allen Texas, donated this instrument to us. Then it gave it back. So the only thing that it does, right? Now the reason the vents are hooked up to these, and they're pulling all the time, same flame. All the atoms that are analyzing point out of theirs. So analyze take them, we're starting to go down. But on this one, it works the same way. There's the furnace is right here, and the sample will be pulled out of one of these trays. This one is a little bit more automated. It's a newer instrument. That instrument was purchased in 1991. This one was actually made in 2004. The lights are a little newer, and this one has we'll switch elements on that. So the spray that's around the 6-year plant. Now the mobile fan, Slovenian land, they're fairly expensive. So this one is a combination lamp. So it does copper, iron, maybe 15. The lead, they're on the low end, $5 to $10. They're done for $800. Get a precious metal. Lamps. So same process. This one is for the flame. This one was used in a smart lab. And now they ran 7. The newer technology came out. The problem was when it heats up, hang up 5 minutes in. They're about the technology of your make your money in quantity, $100,000 cost of initial. They did. Actually, yes, sir. Nobody's president is part of Houston. Set it up. I don't know if the bill would use that, but I had it on in 5 years. And that time of Tony was saying no. The elements of the gas. Then this one you get a larger amount of heat in, and it's sample or protein. So it's all heavy. Like that. Right. The other thing I did point out, because of the current that's going through this thing, the thing down on this end is a big box. It's an electrical transformer. That furnace to produce the heat, it has to pull 100 amps of current. And just to give you an idea, this room has a 20 amp breaker for the entire room. And that runs the light switches, the fans, the everything. To run a graphite furnace, you typically have to have either a 240 amp or volt circuit coming in or a 440. So it takes a lot of energy to accomplish that. Okay, so I hit you with all the clickers at once. So compare graphite furnace and flame. Which statement's true? Right. Okay. I hope it's A. Yeah, it is. So it takes longer. Graphite furnace needs microliters sample. Flame needs mils. The sensitivity, I'll show you on the next page or next couple of pages, is far better with the with graphite furnace versus flame, and they both operate about the same temperature. So you run 24 to 2800, something like that. If you have to have a higher temperature, you can run nitrous oxide in a furnace. Jump to slide. Okay, so now we've got our ways that we're going to atomize our sample, either the furnace or the flame. Let's talk about the analysis itself. I don't hit this thing. If we look at what we can do with the atomic absorption spectroscopy, looking at that side of the technique, it's capable of telling us an element, but again, we can't determine oxidation states, but we can do the analysis of about 70 metals. It tells us total metal concentration. It doesn't matter what the counter ion is, and it doesn't matter if the metal is free, complex, or in the form of an organometallic. So it gives us some information, but sometimes we'd like more. The major disadvantage that atomic absorption spectroscopy has is the lack of information on chemical. So going back to this guy up here, and also there's no speciation. When I say speciation, it doesn't know if it's iron 2 plus or iron 3 plus. It just knows it's an iron atom. The second disadvantage is that you do one element at a time. So if you're trying to find out what's in a sample for qualitative analysis, what's there, it's not an ideal technique. It's used more for quantitative analysis. So the almost exclusive use for it is you know what you're looking for, you take that individual sample and you analyze for that element. Okay. If we look at the radiation sources, what we need is those sources need to be very specific. Ideally, we want an emission band from a source that's narrower than the absorption lines inside of the flame. And in the flame or the furnace, we talked about the Doppler effect, the different things that can occur, Boltzmann's distribution. You have line widths of atoms that are absorbing in the neighborhood of 0.02 to 0.2 nanometers. And that's typically narrower than you're going to get from most monochrometers. Only your highest end monochrometers give you lines that narrow. So Beer's law requires that the absorption signal, the thing that's the light coming in your sample, be narrower than the absorption peak. So if you think of this is my sample that absorbs, all right? So whatever width this is, maybe it's 0.2 of a nanometer. For that to be linear with Beer's law, we need to have the light source be much narrower than that. And the idea is that we want it to be in a region up here where the molar absorptivity is not changing. If I had a source that had a very broad signal, so let's say my source was this broad, okay, and the light I was putting in, what would happen in all these different regions, at every point in that, the molar absorptivity is going to be different. And when that happens, the molar absorptivity changing, that's going to cause a deviation from linearity with Beer's law, where concentration versus absorbance, we expect it to be linear, it would cause it to deviate very rapidly from linearity. So if we want a straight line, we need to have a narrow signal associated with that. So even our best monochrometers are not going to give that narrow of outputs when you get down to 0.02 of a nanometer. So the way we deal with it is we come up with a source that has very narrow emissions. And what we do is take an atomic vapor lamp, and we use a filter or the monochrometer to isolate one of the few lines that come from that atomic vapor. And what happens is the sample absorption has a greater effective bandwidth than that element. So if I'm analyzing gold, I use a sample of gold as my source, and because it doesn't have the band broadening inside of the source that happens in the furnace or the flame, the line's going to be narrower going in. So here's kind of an idea of what's going on inside of an instrument. So you have a lamp. In this case, a lamp is a emission lamp for nickel, and we're going to talk about the lamp. It's called a hollow cathode lamp, or an HCl, in a moment. It emits a signal for nickel. So it's nickel atoms in here that have been excited, and these are all the different lines that nickel emits in. And I use the monochrometer to isolate just this particular region. I'm interested in this window of it. And I shine that light through a flame that has some nickel atoms in it. Here's the absorption line for the nickel. All right, so as it passes through the absorption, the signal decreases. So this signal went from P naught to P. It got smaller because the nickel absorbed. And take the ratio of those two, take the log of it, get the absorbance. So at the burner, what it would look like is that the solvent would have an absorbance, and then I aspire the sample into the flame, and then there's going to be an absorbance, and then it would fall back down if I went straight to the solvent. And this thing down at the bottom, with that being static and moving, not a straight line. A flame's not something that's solid state or steady state. I mean, it's moving around. So what we end up doing is we integrate over a long period of time and get an average. So we'll average a signal anywhere from maybe 2 to 10 seconds and take that average signal. And instantaneous signals not going to be a good reproducibility, because at one spot it may be up here, the next spot it may be at that minimum. That may vary 5%. But by taking a average of a good period of time, and if you have plenty of sample, average for 30 seconds if you want better reproducibility. That's no problem. So that's kind of the guts of the instrument. The monochrometer, what it's doing is it's not selecting the wavelength in terms of creating the band out of the focal plane like we talked about in the previous chapters. The job here is now just to block all the other lines off. Okay, the sharpness of the line comes from the resonance peak of that element. So if we look at the types of source we use, the source is the hollow cathode lamp, an HCl. It's the most common for atomic absorption spectroscopy. These have a tungsten anode sealed inside of a tube that's got either neon or argon in it, and that's at a reduced pressure, so there are only a few torr of gas inside of there. And the cathode is made out of the metal of interest. So if I'm analyzing for gold, I'm going to have a gold cathode. Here's what one of these looks like. I'll let you look at it and then hand it around. You'll see on the next page. So try to hold it not on the glass part, but down the end. The glass envelope surrounding it, let me go forward to you can see this. The glass envelope here is something that's just glass. Here's our tungsten anode, and the cathode is made out of the element of interest, or at least a coating on it. So at the end, since most of these do UV, you've got a piece of quartz put on the end so it can transmit UV glass. And the process that's occurring is that the gas is going to be ionized, the argon or neon that's in there, under a couple hundred volts, and it's going to be a milliamp current associated with it. And when this gas is ionized and it produces, let's say, argon cation, the argon comes running into the surface, and as it comes running into the surface, it strikes the cathode. So this is the cathode material here, and it's going to eject off the metal of interest. So When the cation comes in, it causes the ejection of the metal atoms that are on the surface, and one of those metal atoms gets ejected off, and it's a neutral metal atom. And then inside of the where this electrical discharge is occurring, it can cause the ionization or the excitation of this ground state metal atom to the excited state. And as it goes from the ground state to the excited state, it falls back down. So you've got the metal that's in the excited state, star, falls back down to the metal in the ground state. And when it does, it gives off the emission spectra for that particular element. It's working the same as a discharge lamp. So like you would have on a mercury vapor street light, it's the same process with that. You just need a way of getting that particular metal into the vapor state. And that's what the neon or the argon does, is that as those gases become ionized, now it's attracted to the cathode. It comes flying in here with a lot of kinetic energy, and it dislodges that metal of interest. So it dislodges the metal absorbs energy and gets converted to metal excited state, and the excited state goes back down to the ground state by emitting a spectra off, a light spectra H2. So the good thing about them is they're very specific. If I have a, what is the element for that one? I don't remember.
Cadmium.
Okay, so cadmium is a toxic metal that we have to really be concerned about. The bad thing about cadmium is it's being used in electronics all the time. Okay, in the periodic table, cadmium is doped into silicon all the time. It's close to the metalloids in the center. It changes the properties of silicon and makes it a conductor. So the cadmium's used a lot in the metals industry. But cadmium is a very toxic metal in terms of its bioactivity inside of the body. Part per billion levels of cadmium, long-term exposure are lethal. And you really have to be careful to any exposure of cadmium. So this is very specific for cadmium, that source is. It emits a spectra that exactly matches that of cadmium. It's a very simple design. All you need is a couple 100-volt power supply to run it. The problem is that every one of the lamps, or each lamp is unique for every element. So if I want to analyze 20 different elements, now I have to have 20 different lamps at 800 to $1,000 a piece. The faculty member that was here before us, he did his research with that, and right behind us on the bottom table, I think there's 24 different lamps there. There's $25,000 worth of lamps sitting in there because he has precious metal lamps as well. You may buy an instrument that costs $40,000, but the accessory kit with it to analyze the elements you want may be in excess of $20,000. It's just something you have to think about. If you're interested in only doing one element, arsenic, lead, whatever it may be, mercury, you can buy that single lamp. Another problem is that self-absorption can limit the output intensity the same way we talked about with a laser. The energy that's going to be emitted off the thing, as it goes from the excited state to the ground state, and you have this emission that's given off, H nu, it's going to be exactly equal to the energy that would be absorbed if it goes from the ground state to the excited state again. So the idea is to get the light out of the instrument, out of the tube, before it can be recaptured by itself. All right. One of the problems that we have is dealing with the light that comes from the flame itself. So to deal with this, if anytime you have a flame that's glowing off colors, those colors could interfere with analysis. So if your sample gives off orange light and that orange light was going to interfere with analysis of your metal, the way that you deal with this is source modulation. So emissions from the flame can be eliminated by modulating the source, the output of the HLC source, so that it fluctuates with a constant frequency. So you imagine having the lamp, and you've got this chopper, which basically looks like a fan blade with slots cut in it, and you're going to have your light where it's transmitting through versus being blocked. It's transmitted through or it's being blocked, and transmitted being blocked as it spins around this rotation. So when it's being blocked, none of the light makes it through the flame. You're looking at the burner emission only. So this signal is due to just the flame down here at the bottom. And the top is the combination of both. Your analytical signal is simply the difference in the two. So you can take an electronical circuit called a difference amplifier that looks at the square wave and looks at the difference in the square wave signals and amplifies just that difference. So basically it does a subtraction before it analyzes it. So your detector is going to see an AC signal from the two sources, that from the lamp and the flame, and that from just the flame itself. And typically you do a run through a high pass RC filter and remove the unmodulated DC signal out of it, and then pass it through an amplification, which is just going to amplify the AC signal in that particular environment. All right, so if we kind of now look at the different types of analysis and compare back to the different ways that we can do these, we can look at emissions. So if we want to do emission spectroscopy, we can just get the sample hot in the flame, it emits off a signal, and we can analyze that light and take it into a detector. When we do, so this is going to be flame emission, and these are labeled down in the bottom. So this is flame emission spectroscopy. All right, and then if we look at our flame AAS, is where we're going to look at absorption. We're going to take the light from a source, run P naught through, and look at how much is transmitted through, and then quantify based on that. Now, if we want to get really, really good sensitivity, we can take the inherent sensitivity of fluorescence. We can take a laser and shine that laser beam into the flame. Okay, from that we have an excitation, so our P naught is being used for excitation, and the sample gets excited and it emits back off. It's going to emit off at the same wavelength, but we look at it at a right angle, and we can take that, isolate that particular wavelength, and we can have atomic fluorescence. Now, sometimes in fluorescence, if we think about absorption, it's just the capture of light. In emission, it's just looking at light that's given off, going down. In fluorescence, we have both an excitation event and an emission event. So the one where the two wavelengths are equal, lambda excitation equals lambda emission, that's what we call resonance fluorescence. But sometimes you can have a non-radiative decay, it bumps into something, and you could have the Stokes shift. So this delta E that would be entered to this would be the Stokes shift. But we don't have that very often with atomic species, because those are usually molecular and rotational energy losses. So most commonly what we're looking at in atomic species is resonance fluorescence. Lambda excitation equals lambda emission. But because we can focus in the energy of a laser, some elements that don't work well for atomic absorption, we can see them in really, really high sensitivity in emissions. All right, looking at the instruments. So precision and accuracy of atomic methods depend critically on the atomizer and the control associated with those. You can buy a very, very low-end atomic absorption spectrometer that uses a diode array detector. It's got one single lamp in it, and you can get something like that for about $3,000, all manual controlled, no robotics whatsoever. Or you can buy a fully robotic one that multi-element would switch automatically, and something like that would cost in excess of $100,000. You can use filters to isolate the lines for 22 different metals. So if I know I just want to do lead analysis, I don't have to have a monochromator to isolate the line for lead. I can use a filter. A filter costs me $100. So I can have a hollow cathode lamp, isolate that filter. There's nothing else frequently that's going to absorb there that's going to interfere. So there's no cost of a monochromator, which is typically minimum $10,000 in the cost of the instrument for a high-res monochromator. And then I just have minimized electronics going there. And on a low-end instrument, I'm going to have a photodiode as the detector. Most common instruments today on the higher end are going to have a photomultiplier too. So better instruments are going to have a monochromator, and typically it's going to be a pretty good one, at least a tenth of a nanometer resolution. So its idea is it's isolating that that band of interest. So you've got your hollow cathode lamp. That's your source. You shine your light from that into the atomizer. Sample is going to be introduced into that flame somehow or to the furnace. Then you do your wavelength selection after the fact. And once you choose what lambda X is, you put that that wavelength in the detector, and then you process the data from that. So here's two different designs that we have on instruments. Lower end instruments are going to be single beam. So the light from a single beam instrument is going to come from the hollow cathode lamp, pass through the flame, run through a grating, and then into our detector, whether it's a phototube, a photomultiplier tube, or a photodiode. Higher end instruments, like both of the ones we have, they're going to modulate the signal by running through that chopper. And as it runs through the chopper, it creates that square wave AC. And from that, some of the times the light's going to go through, sometimes it's going to pass. Typically, you have a mirror, and then 1/4 of it is going to be partially silver. The other, the light transmits through. All right, it's going to be the same thing on this side, and the two things are going to be exactly out of phase, whether it reflects the light or allows it to pass through. Then it just goes through wavelength selection. And because of the frequency associated with this chopper, you know how fast it's spinning. So if you set it to spin at 500 hertz, you can tell the amplifier just to amplify the signal at whatever that square wave AC is. 500 hertz, 1,000 hertz, whatever. And it will amplify only that signal into the system. So it's a pretty developed technology. They've been using these constantly for a good while. In terms of interferences, what causes problems? There's a couple of different things that cause issues. They're either chemical or spectral, and we're going to look at both of those. We're going to start with the spectral. Spectral is where you have an absorption or emission of something that either overlaps with the absorption of the analyte or that the monochromator can't separate the two. So you've got signals that are overlapping on top of each other. So if you look at vanadium's absorption at 308.211 nanometers, it interferes with a signal from aluminum that's at 308.215 nanometers. So that's only 0.004 of a nanometer difference. You can't resolve it, so what would you do if you were analyzing aluminum? You would just go to a different line for aluminum. Okay, so every element has multiple lines. You pick a different line. Occasionally, combustion products can absorb, but we can correct for those by doing a proper blank. One of the biggest problems that we have is the sample matrix. It can be a pain in the butt more than any other technique that we use. Here's an example of, let's see, where's my sample matrix example? I'm going to go back to, or find that question in a second. I got my slides out of order, I'm sorry. Okay, so here's the example of the sample matrix causing a shift in the analysis. So here's strontium in water, and here's its calibration curve. And here's strontium that's added to aquarium water. So sometimes aquarium water can be pretty nasty. The big thing is now you look at the difference of the slopes are not the same in the two lines. That difference in slope is an interference. So if we do a calibration using standard additions calibration, so that's what this is we take the matrix with the sample in it, and we analyze it, and then if we look at this signal, and we add known amounts of strontium to it to create a calibration curve. This is standard additions. And then we take that and go back to where it intercepts at the x-axis. The x-axis says it's at intercepts at negative 7.41. That means that the concentration of strontium is equal to 7.41 parts per million. You take the absolute value of that intercept. But if I'd done the same thing and compared it with a regular calibration curve, so if I'd done, this would be called an external calibration. So I would standardize with a set of standards that I made up, and now compare those to my sample. With this one, my signal would be about like this. I drop down, and I would say it's somewhere approximately 5 parts per million. So the difference between the true 7.4 and the 5 is an error that's been introduced by the matrix in this. So whenever we can, or if we're uncertain about it, we do standard addition. Now, way back in chemical analysis, I talked about ways to check for what type of error would this be called? A systematic error or a random error? Systematic. Okay, so this is a deviation from the truth. So this is a systematic error. And there were ways for check for the systematic error. You could run a known sample, so a known standard. All right. You could analyze, run a blank. It would tell you something about it. If you ran just the matrix itself, does it give you a zero signal? You could run a sample spike. So you could spike it or fortify it with a known amount. So you can analyze the sample, and if I added 2 parts per million to it, did it increase exactly 2 parts per million? There's a bunch of different ways. Standard reference materials. There's a lot of different ways to deal with that, to be assured that you're looking at or getting really the right signal in your analysis. All right, but going back to the interferences, so we have the spectral interferences that we can run into. Here's another example of a spectral interference. This is barium that can exist in alkali or earth mixtures. So what happens if I'm analyzing for barium? Barium has this resonance line at 553 angstroms. That's where it's most sensitive at. But if I've got calcium in my sample, calcium forms a stable hydroxide that absorbs under this wide band and emits at this wide band at near the same wavelength. In fact, it's right on top of it. So what I have to do is to get rid of that is apply enough of a heat treatment that I can destroy the barium oxide. And we can do that by using, nitrous oxide for a heat treatment. So we hit it with some laughing gas, N2O, and that takes the temperature from about 2600 up to closer to 3000, and that high temp destroys the calcium oxide. So it eliminates this in the signal. It lets us look at our pure barium signal isolated. So sometimes heat's the better thing to do. The chemical problems are trickier to deal with. They're more common than spectral because there's a lot of chemical interferences that occur, and these can be minimized by choosing the correct operating conditions. We have to realize that when a flame is burning, it's working as a solvent in which chemical reactions can occur. And there are 3 types of inner equilibria that causes problems in our system. So you can make compounds that have low volatility. We can have dissociation reactions, so something forms a molecular form. It's no longer in the atomic form. And the other thing that gives us a problem is that ionization events can occur. So talk about each one of those. Things like low volatility. This typically, when you have inorganic ions present, things like phosphate in particular is a problem. Those will form low volatility complexes and reduce the rate of atomization that occurs. A couple examples are calcium in the presence of phosphate or sulfate forms a stable heat complex. So 3000 degrees won't treat that well. Right? If you have magnesium in the presence of aluminum, those 2 things form a very heat stable compound. And you've got to take it up to above 3000 degrees to break that up. So we can take the temp up higher, and we can try to break it up with high heat, or we can do a chemical treatment. Something like lanthanum oxide, it would remove the interferences from phosphate because it binds with phosphate almost irreversibly. So in your sample pre-treatment, you could get rid of the phosphate by adding some lanthanum to it. That way all the phosphate's going to be tied up with the lanthanum because it has a higher affinity for that metal than almost any other. Dissociation equilibriums are typically when you form hydroxides or oxides with our metallic species. So we're trying to get in the form of our neutral metal, okay? But If we have an ionization event that can occur, instead of being our neutral metal, the metal, while it's ionized in the form of the digestion, almost always we take a sample and we dissolve it, it's in an ionized state. So inside of the flame, before it can be converted into a neutral form, you can have that react with oxygen and form a metal hydroxide, or metal oxide, or form a metal hydroxide. So water inside the flame is burning. There's going to be a lot of hydroxides around as well as oxide ions. So things like titanium and aluminum, they're very troublesome because of the oxides that they form. Now we can overcome that a little bit if we use a fuel-rich flame. That's going to minimize the amount of oxygen that's in excess. If we take those concentrations down, Le Chartier's principle says that the equilibrium is going to run back in this direction, okay, shift to the right, so we can make the equilibrium go to the right and minimize those interferences by controlling the flame to some extent. Now, that's an advantage of the graphite furnace, because in the graphite furnace, you've got an inert atmosphere. You've got it in argon. There's no oxygen around. So you don't have that interference in the flame. Another problem that we have is ionization events that can occur. And ionizations become a problem when you have an excess of free electrons in the flame. So we're wanting our sample to be in this form. So if we have something that ionizes very easily, what we can do is add an ionization suppressor to it, which adds a high concentration of electrons. So a common thing to use is something that's got a lot of chlorine atoms in it. Any of the halogens work fairly well, or bromine, and when they burn, they yield off a high concentration of electrons, and that high concentration of electrons drives this equilibria back into the form that we want, into the neutral atom. So we can minimize ionization by putting an ionization suppressor in our source. And a lot of times we'll do our digestion in something like 1 molar hydrochloric acid. And it's there for a couple of reasons. The acid, high concentration of acid, helps break the sample up, applied to heat. But the other reason is this 1 molar chlorine present works as an ionization suppressor when we do the analysis. We just have to make sure we have that in our blank as well as our samples and our standards. Right, this shows the example of an ionization suppressor's influence. So this is the suppression of the barium ionization that occurs by the addition of an ionization suppressor to potassium. So potassium's added as the ionization suppressor in it. So this is our barium signal. That's its absorbance. So its absorbance is very low. This is the barium resonance. This is the barium line. So this is the barium cation. So this guy is the barium cation, where this other one is the neutral barium, right, the zero state. So what happens with just a solvent itself going into the flame, I've got a very low signal associated with it. But if I'll start adding more and more potassium in it, potassium's easily ionized to potassium plus 1 cation. It's got a low first ionization energy, gives an electron off, increases the concentration of electrons in the flame. As I start to add more and more until I get to the point about 2,000, and 2,000 parts per million is not that much. Okay, that's 0.2%. So 2,000 ppm is equal to 0.2% weight. I can easily make that up when I digest a sample, put that much potassium in it. So after that, I start to saturate the amount of electrons that are needed to drive the barium in the form of the barium knot in the analysis. Okay, so a rich flame would do what? So we said what rich was a while ago. Right. So we're going with C. Yep, C. So the rich flame is going to be cooler. A rich flame is going to decrease the electron concentrations because there's not going to be as much oxygen around. Well, it does decrease the amount of metal oxides that are formed. Because there's less oxygen, it drives the equilibrium in the reverse direction. All right. Background absorption, how can we correct from the background signals? We're going to talk a little bit about that, and this is going to be pretty much where we're going to call it quits today. We're going to get where we can finish up with the emission spectroscopy on class tomorrow. So background absorptions are a major problem that we have because not all of the samples in the sample matrix are completely atomized. And if we have molecular species that leave small fragments that can absorb and emit below 250 nanometers. So what we do is one of the ways that we can correct for this is called continuum source background correction, and it uses a deuterium lamp. Both of the instruments that we have next door have this correction in them. So what happens if the slit width is set at 0.2 nanometers? The continuum from the background of a deuterium source fills the entire window, and it allows for a background correction. So kind of got to just follow what's going on with the, if you got a sample that doesn't absorb at all, so this is the slit width that we see, right? And this is the signal actually from the atom. So what we're looking for is when the sample absorbs, this is decreased. So it would be this little gap in our continuum or at our spectral bandwidth that we can see. And if we look at how much signal the background absorbs out of that, we can look at the atomic absorption versus all the background absorption by looking at the difference in these two things. So that is a way we can correct for any background emissions and absorptions that are coming not from our particular atoms at the narrow bandwidth. Another way that we can correct for it, and the instrument that was on this side has this correction, is called the Zeeman correction, and it uses a strong magnetic field to introduce new energy levels. So the same way with NMR, nuclear magnetic resonance, you get the splitting of the spin of the nucleus only when there's a difference in those energy levels, only when there's a magnetic field present. And the stronger the magnetic field, the further and further those energies are apart. Okay? Here we apply a magnetic field, and it's looking at the spin of the electron. So the energy of the spin of the electron is the same if there's no magnetic field, the upspin versus the downspin, but when we can put a strong magnetic field in there, we can separate those energy levels apart. So what happens is that each energy level interacts with polarized electromagnetic radiation differently. So this is the mercury line that appears at mercury's resonance 253, and we can apply the magnetic field to that, and it splits that into three separate lines. We can look at the difference in that shift to make sure it's the shift we expect of one signal versus the other signal, and know that the signal that we're looking at, I'm expecting this signal to cut in half or 50% or whatever that is. If it doesn't, I know there's a possibility. And by looking at the ratios of these two signals, when I have a split signal, I have a very high confidence that this split signal is really due to my particular compound that I'm looking at. So the Zeeman effect, it's high in accessory. Typically, a Zeeman, the magnet itself and the power supply with the magnet is a $10,000 luxury add-on. Where the deuterium source is typically a couple of $1,000s to have a deuterium background selection or correction. Zeeman's the Cadillac. Here's kind of the idea. You take your light from your hollow cathode lamp and you run it through a polarizer, which only is going to let light with a certain polarization pass through. And when the sample is placed in a magnetic field, so you've got a magnetic field, so B, notch your magnetic field, what that'll cause is this separation of light into the three different bands, and only when they match up with the polarization of the light that's exactly right, then will the sample absorb. If it's unpolarized, not in a magnetic field, it won't absorb there. So you have a correction based on that where you can look at a background versus the background plus the atomic absorption, and you can correct for the things that are due to just your atoms that interact with that magnetic field in that particular way. So that's the Zeeman detectors, and it's a nice, if you're doing critically important work, so something that's going to go to like regulatory analysis, Food and Drug Administration, almost always you're going to have some type of high-end background detection. And Zeeman's one of the most common things that we do. All right, sample prep. I'm going to go ahead and talk about this today. So I've got this put on just a couple of slides. When we have to take a sample and get it into a liquid state, that's not always trivial. A lot of times our sample won't go directly into a solvent. So if you take a chicken leg and you throw it in some water, it will soak there for days and days and days, and very small amounts of that dissolve. So what we have to do is go through some type of a process to convert a solid sample into an aqueous phase or a liquid phase that we can put inside the instrument. So typically you're doing this by decomposition and dissolving with a proper treatment, and that treatment is called ashing. You can do just a direction application of heat, and like you would burn a sample in an oven, but you can do it in other ways as well. The most common one is a hot mineral acid. So you subject the sample to nitric acid, hydrochloric acid, sulfuric acid. In the case of samples that have gaseous components, if you have to dissolve silicon dioxide, glass, you have to do that with hydrochloric acid. Now, hydrochloric acid is a problem because it dissolves glass. So you're not going to use a regular beaker. Everything has to be a Teflon lined container, has to be a special hood, because hydrochloric acid will react with certain metals and make an explosive compound. So HF is a problem to deal with, but if you're dealing with looking at samples that are like rocks and have a lot of silicon dioxide in them, that's what you have to use. But normally we use nitric acid, hydrochloric acid, or some combination of sulfuric. We can do liquid oxidation. So I don't know if y'all remember the experiment that we did last year. We did the analysis of iron, so we dissolved the iron sample or the steel sample in nitric acid, and then after it ran for a while, we took the steel sample and we added some very strong oxidant to it, and it took the carbon that was left in there and converted that to CO2. Okay, so that was a liquid oxidation that occurred. You can take a sample and you can put it in a bomb, like a bomb calorimeter, so put a very high concentration of oxygen there. If it's a carbon sample and you could ignite that and it would burn, you could collect the dust from that or the ashes and you can put that in solution. And the last statement I have on here is something that's the methods development for sample preparation is an art form. I mean, you really can, if you want to screw up an atomic technique, this is your opportunity to do it. You don't get all the sample dissolved. You convert the sample into some form that you can analyze. There's a lot of ways to screw up. So the thing that I encourage you to do, if you're ever in an opportunity to do this, go by something that's proven. So don't freelance a method. Go to the literature, go to a book and find a way to look at it. I mean, there are literally textbooks written for individual element sample preps. Ways to analyze for lead. And it will be a 300-page book on different ways if it's lead in this versus that, and the different ways you can analyze it. It's really intricate and tricky, and it's one of the things that makes this a lot more complex than we think. So calibrations, we want to try to make the standards and samples have a similar matrix. That if you don't know what your sample matrix is, that's sometimes difficult to do. A traditional calibration curve is going to have 3 or more standards associated with it. We have to be aware, especially when atomic analysis, that what is your linear dynamic range? Every one of these techniques with the metals analysis is going to reach a point when you go concentration versus absorbance, you're going to lose linearity in the system. Okay, so it may start off nice and linear, but typically you get an order of magnitude and then it's going to start to deviate from linearity, and soon it's going to flatline. So we want to make sure that we're in this linear range, the linear dynamic range, whatever this window is. That's where we want to be doing our analysis at. So if our sample, when we measure it, has an absorbance higher than that. So if this is my upper limit of the absorbance, so upper limit to the absorbance, if I analyze a sample that's anywhere above here, I have to dilute it to get it down into a useful range. I dilute it 1 to 5 and reanalyze it and see what I get. It's not a problem to do. You just have to be aware of it. Our technique that gives us more assurance is standard additions. So we can remove chemical and spectral interferences by analyzing a sample that's been spiked with standards, and we know how much we've added to it. But now you've got to do a lot more sample prep, because you're not just making one sample up, you're making the sample plus however many different calibration points you have. But modern instruments today can do the standard addition automatically with the robotics, and they can take the work out of this. So I showed you the example of the standard addition. You did the strontium, and then an instrument came back and added 2 parts per million, 4 parts per million, 6, 8, and 10, and did an additional 5-point calibration. The problem is you have to do the calibration with absolutely every sample. So instead of now analyzing one sample, you're analyzing one sample plus 5 spike samples. So you've got 6 times the amount of time versus doing a single sample. If the robot's working 24 hours a day and you don't care, that's fine. If you're manually sitting there pipetting everything in, it sucks. Especially if you have to get triplicates. So now, if I have to get 3 of something to get reproducibility, now I'm doing 16 different analyses. So, you know, there's goods and bads to everything. Okay, I'm going to quit here. This is something just to show you detection limits and nanograms per milliliter. What's a nanogram per milliliter?
Per billion.
Yeah, it's a part per billion. And what the different techniques are capable of doing of. So we've talked about the flame techniques versus the electrothermal. So most of the metals in flames are in the low part per billion level. Some things like mercury are not that good. Arsenic's not that good. But most of them are in the few part per billion level. Electrothermal gives you much greater sensitivity because the sample now is exposed to the light much longer. So in this example, going with aluminum, you've got 300 times the sensitivity going from the flame to the furnace. Things like calcium, it's only a 1 to 4 gain. It's not that good. But cadmium, something that's toxic we need to know about, it's giving you 100-fold sensitivity. A lot of them give you a minimum of 100-fold. For that reason, if I need high sensitivity work, furnace is the way to go. Now we'll talk about flame atomic absorption, or flame emission, and ICP will be the focus that we'll look on class on Wednesday as we finish up the notes. There's 24 slides left. We'll be able to do that one day, no problem. So we'll finish this up on Wednesday. But element to element, there's a lot of variation. So there's no perfect technique that analyzes all of them to great detail. In general, the emission techniques are a little bit more sensitive than most of the other techniques. But there are examples like if we look at calcium, if I really want to see calcium low, the emission spectroscopy and the ICP is the way to go. But that would be 0.1 parts per trillion. You're never going to find a sample of that has that little calcium in it, because calcium's everywhere. It's one of the most abundant elements that we have on the Earth. So it's in the top 5. So there's a lot of times these elements, even though we can reach these low levels, you're never going to run into a sample with that low of a concentration. It's the toxic things that we're concerned about, where we need to know the very low concentrations. Okay, so